Good morning. We'll start the lecture today with a review of the common source amplifier from 310. This is a very simple circuit. When we have a common source amplifier with resistive load, it consists of a MOSFET, a resistor, and that's it. So a resistor R between the supply and the drain of the MOSFET. The input is at the gate of the MOSFET, and the output is taken from the drain of the MOSFET. This is the supply. Now the input VI is some DC voltage plus a signal because I need to make sure that the MOSFET is biased in saturation. So the DC component of VI bias is VGS DC for the MOSFET, and this should be greater than VT. And the choice of VDD and R would make sure that VDS is greater than VGS minus VT. So this should be in SAT. MOSFET is in SAT. This is this is the DC condition. I don't have numbers, but I can easily find the DC current. So if I know VGS DC, the DC current would be half K VGS DC minus VT squared. And then I can find VDS, make sure that it's greater than VGS minus VT. And I can find any quantity I want. I can find there's not much to find here. There's VDS DC, there's the current in the resistor, which is the same as the drain current. So the important quantity would be ID. And ID, we find it from DC analysis in saturation. This will give me a GM, right? ID over half VOV, of course, ID and VOV, which is VGS minus VT, so GM and RO. So this is the DC analysis. We get GM and RO, and then we can do the small signal analysis. And the signal analysis, we find the quantities of interest. This is an amplifier, and we already showed that this is an amplifier in the 310 when we did the transfer characteristics, and there was a nice region on the characteristics where there is large slope, almost linear characteristics, and a good range. So we know already that this can be used as an amplifier, and if it can be used as an amplifier, it means that I can model it as an amplifier. So to model it as an amplifier, I need three quantities: the voltage gain, the input resistance, and the output resistance. So from the signal analysis, from the small signal analysis, I should be able to find these quantities. These are signal quantities. Now, also to review, the voltage gain is AV, which is the output voltage, the signal component, and the output voltage divided by the signal component and the input voltage. But what enters in the model of the amplifier is AVO, which is VO over VI, or AV, when RL is open, when RL is an open circuit, that is, there's no load. Here in the circuit, there's no load. So when we calculate AV, this will be AVO. And the second quantity is the input resistance, Ri, which is defined as the input voltage divided by the input current. And the third quantity is RO. And RO is not the output voltage divided by the output current. RO is, we connect a test source, Vx, and from this test source, a current Ix would flow when we connect it at the output, and we set the input to 0. So if there is a load, we disconnect it. The test source replaces the load, is connected where the load was connected, and the input is set to 0. So VI in this case is set to 0. All right, and then we find the value of Vx over Ix, the test source voltage divided by the test source current. Okay, so let's start with the small signal analysis. In small signal analysis, the DC source becomes 0, or any DC sources become 0. The MOSFET is replaced by its small signal model, and the resistor stays as a resistor. The small signal model of a resistor is same as the large signal model. So this is the input, VI, and now I have signal quantities, so small letters. This is ground. This is VGS. This is the gate of the MOSFET here. So that's the input at the gate. And then the MOSFET small signal model, GM VGS. The source is grounded. So GM VGS. This is the source, it's at the ground. This is the drain. And also I have small RO from drain to source. And then R is connected from drain to the supply, but the supply in the signal analysis becomes 0. So it's like ground. And R is therefore in parallel with small RO. And the output voltage is between drain and ground. So it's across the parallel combination of R and RO. By the way, if you have any questions, raise your hand in Zoom or type in the chat window. All right, so this is the small signal model. Now I need to find the quantities. Let's start with the very easy one, which is actually the input resistance. The input resistance is very, very easy to find. Why is that? Because there's no input current. This is the input voltage, and this is the current that we call the input current going towards the amplifier. So that's the input current. Now, obviously, it's 0 because there's an open circuit here at the gate. So because II is 0 and VI is some signal voltage, I can very quickly say that RI is infinite because II is 0. That's easy. What about the voltage gain? Well, if you look at the parallel combination of R and RO and consider it as just one resistor, then the current GM VGS is flowing like this, and then back, and then it flows up in the parallel combination of R and RO, which means that the voltage VO at output is, because the voltage is plus at D and minus at ground, and the current is flowing up, then this means that the voltage is the resistance, which is the parallel combination of R and RO, times the current, GMVGS, but GMVGS is flowing up, so I need to have a minus sign there. So minus GMVGS. But VGS is exactly equal to VI because VGS is between G and S, and VI is also between G and ground, and S is ground. So I can rewrite this as minus GM R parallel RO times VI. So this is what happens at the output. Now, if I divide, I get AV equal VO over VI. And that's minus GM R parallel with RO. So this is the voltage gain. And in this case, as I mentioned, this will be also the open circuit voltage gain because there's no RL. If there is an RL, AV and AVO will be different. And to find AV from AV, to find AVO from AV, I set RL to infinity. All right, what about output resistance? For output resistance, I need to connect a test source across the output terminals and set the input to 0. So for RO, VI, I set it to 0. If VI is 0, this implies that VGS is 0. And if VGS is 0, this means that GM VGS is 0. Right? So the current source is now an open circuit. So imagine a test source across the output terminals and you want to find the resistance Vx over Ix. The current Ix that will flow out, actually the test source would be connected like this. And across its terminals, there's only, so this is Vx, and this is the current Ix. And after I set the input to 0, this will be an open circuit. There's the GM VGS would be an open circuit, so there is nothing. And I will have left R in parallel with RO here. All right, so that's it. What is Vx over Ix? The output resistance, it will be R parallel RO. So RO would be R parallel with RO. That's the output resistance of the amplifier. So these are the three quantities that we're usually interested in, the voltage gain, input resistance, and output resistance, and we just found them for this type of amplifier. Now, if I want to build a better amplifier, usually after more gain, sometimes I need to do other things, like I need to have a better amplifier in terms of maybe power or in terms of distortion or input resistance. But usually, if after amplifying, the most important quantity would be gain. Is your gain large? Is your amplifier really amplifying a lot? So let's look at AV and see how we can enhance it. It's minus GM R parallel RO. So I have two quantities from the MOSFET, GM and RO and R. And if I want to make it larger, if I want to make AV larger and larger in absolute value here, I want to make the product GM times R parallel RO large. This product is actually bounded. This cannot be bigger than minus an absolute value GM RO. The reason is that whenever you have a combination of two resistors in parallel, the parallel combination is always smaller than the two resistors. So R parallel RO is always smaller than RO and always smaller than R. And here we can identify the first issue with the gain of this amplifier. R cannot be too large, especially if I'm talking about an integrated circuit. In integrated circuits, the resistors cannot be too large because they will take a large area. So we need to keep them small. And if I use the resistor and the resistor is small, and I look at this gain formula, then this small R in parallel with RO, the parallel combination would be even smaller than R. So that's a small quantity that I'm multiplying by GM. So here's why I'm losing gain, because R cannot be too large, it has to be small. So if we want to improve on the gain, maybe we should consider making R very large. And that's the idea that we will try to analyze now. Can I make R really large? Well, the largest R that I can get is an infinite R. So if R goes to infinity, the gain becomes minus GMRO, and that's pretty large. We call that the intrinsic gain of the MOSFET, and this can be in the tens or even hundreds. But how can I make R infinite? I cannot just disconnect it from the circuit, because then the MOSFET would lose its bias, the current would not be able to flow. I can make it large in signal analysis if I use, instead of R, a current source. If I use an ideal current source, then this current source for DC analysis will provide the MOSFET with the right bias. But in small signal analysis, this is an ideal DC current source, and small signal analysis, it becomes zero. And this is the resulting small signal model, or a small signal equivalent circuit. There's no R now. Where did the R go? Well, the DC current source is ideal. And in the small signal analysis, I replace it by an open circuit. So my DC conditions are the same now, similar to the previous slide, but my signal conditions are very different. Now there's no R in the signal analysis. And if I repeat the analysis, the input resistance is still infinite because there's no input current. The output resistance is only small RO because there's no R. It was R parallel RO. And the voltage gain is now minus GM times RO. And this is the intrinsic gain, and this should be a decent gain. There is no RO parallel R, which drops the gain in absolute value significantly. So this looks like a great idea. We can get a very large gain by just replacing the resistor by a current source. So now the question becomes, okay, this is a nice idea. Can you build a current source? Well, yes, we learned how to build one this week. We can do that. So let's have a current source built using what we learned. And if I need a current source here, then this is what I can do. I can replace it. I can build it using this. This is a current source using P MOSFETs. Actually using one P MOSFET, Q2, Q3, and IRF, the other side, the left side. This is usually there. This is the golden reference that I have. Whenever we need a current source, I use IRF with Q3 and mirror it, and I get the current that I need. So if I need the current I here, I'll just mirror IRF using Q2, and I will get my current source. Okay, so this means that I need the MOSFET instead of a resistor. I need Q2 instead of R. Before we continue further, let's see. Let's verify this using PSpice or Spice, and build the circuit in Spice, or write the circuit description in Spice and simulate it, and see how the output would vary with the input, and build the voltage transfer characteristics. And we get something like this. We get the blue curve. And now we need to observe, we need to see if this can be used as an amplifier. And look at the portion, look at the region between points A and points A and B, the region number 3. Region number 3 is here when Q1 and Q2 are saturated. If Q1 and Q2 are saturated, I'm in region AB, in region 3. And it's a beautiful region because it has almost linear characteristics. very large slope, right? The drop is very sharp, very large slope. And the range is pretty good. It's between point B here and point A. So this is very good range. So that's an ideal region to use as an amplifier. And therefore, I can conclude that, yeah, it looks like this circuit can be used as a really nice amplifier. All right, so then let's continue with the analysis of the circuit as an amplifier. This is my circuit, and here I am doing the small signal equivalent circuit, and I am showing so far the input voltage. So the input voltage is here at the gate, and we see it here. So that's the gate. This is G. And the MOSFET is shown with its GM, VGS, and RO. So that's Q1. This is Q1. And then I have Q2, Q3, and IRF. So I have all of this. And I need to find now its small signal equivalent. How would this appear in small signal analysis? Well, we did this derivation, or we know we have a result. We said previously that if you have a circuit like this and you're doing small signal analysis, actually it is just a small resistor, not small in value, just a resistor, and it's equal to small RO2, and it appears between this node here and ground. So this is what we get for Q2, Q3, and IRF. We can model them by just a small RO2, which appears between the output, between the drain and ground. This is the source here. GDS referred to Q1. So the current mirror circuit is modeled by small RO2. And what you see now is the whole small signal equivalent circuit. So GM-VGS, and then I have RO1 and RO2. And you can also see that RO1 and RO2 are in parallel. And what does this mean? It means that the input resistance is still infinite. The output resistance is RO1 parallel RO2. So we're back to the parallel combination of two resistors. This means that the output resistance is not just a small RO, but if the two ROs are almost equal, the output resistance drops to 1/2 of that. So is this better than having an R? It is much better. So let's consider an example. If I have a resistor R, which is 5K, I'm using in my circuit, and RO is 50K. These are typical values. Then the parallel combination of 50 and 5 would be something like 4 or 4 point something. But if I remove the 5 and I replace it with a MOSFET Q2, which has an RO, which is also 50, the parallel combination of two 50s is 25. So instead of having a parallel combination, which is 4 point something, I have a parallel combination, which is 25. So yes, I do have resistors in parallel, but still I would get much more gain. So it's worth the improvement. What about the gain? Well, we can rederive it, or we can quickly just guess that it should be minus GM1 RO1 parallel with RO2. So I get large gain. It's less than the intrinsic gain. The intrinsic would be minus GM RO. This is less than the intrinsic gain, but it's still pretty large. And much larger than having a small resistor there between the drain of Q1 and the supply. Now, instead of showing the whole circuit every time, we can just show Q2 like this with a V bias. So if you have something like this, if you see a circuit like this with a V bias, it means that it's probably coming from a circuit, and this Q2 is mirroring a certain reference current, and this left half of the circuit is basically setting the voltage here to some V bias. And instead of showing the details, if you see a V bias coming here connected to the gate of this MOSFET, then you know that there must be some other circuit that is setting this bias, and Q2 is acting as a current mirror, as a current source for Q1. So this is a simpler way to show the circuit. All right, so the voltage at the gate of Q2 is this V bias. It's a pure DC. And we said that in small signal analysis, Q2 appears as a small RO. In fact, the resistance seen looking into a MOSFET drain with gate and source at DC levels is equal to small RO2 to ground. In this course, we will use this idea a lot. The idea that we don't need to do full analysis of the circuit. We can maybe analyze it by using some rules and formulas. And this is, in fact, the first rule that we will use. So what does the rule say? It says that if I'm looking into a MOSFET drain with the gate of the MOSFET and the source of the MOSFET at DC levels, then I will see a resistor equal to small RO2 to ground only. That's it. So what does this mean? What does looking into the drain of a MOSFET mean? Let's expand. Let's understand what we're saying here. So this is the condition that I'm talking about. On the previous slide, I said the gate is pure DC. So if I'm doing small signal analysis, the gate is at signal ground because the voltage at the gate is pure DC. This means signal ground. The source is also at a pure DC level. So this means that the source is at signal ground. So this is the gate and it's grounded, right? This is ground. This is the source and it's grounded. This is the rest of the MOSFET. This is the MOSFET, GMVGS parallel RO. Now, what does looking into the drain of a MOSFET mean? So I have this eye here that's looking at the MOSFET drain. We use this term and we will use it a lot in this course. Looking into a certain drain, looking into a certain terminal. What this means electrically is as if you are connecting a test source here. So this is the eye really. The eye is like a test source. V test or Vx or whatever you want to call it. And you're finding I test. And the eye will see the resistance V test over I test. So the eye is like an ohm meter that measures resistance, and it will measure V test over I test. So when we say I'm looking into the drain of the MOSFET, it means I'm finding the resistance between the drain and ground. When there is a test source connected like this between drain and ground, V test, I test, so the eye would see this resistance, V test over I test. Okay, so under these conditions with gate at DC, source at DC, so they're both at signal ground, and I'm looking into the drain, so I'm connecting my test source between drain and ground. What is the deal? Well, if VG is 0 and VS is 0, signal components are 0, it means that VGS is 0 because G is at ground and S is at ground. And this also means that GM VGS is 0. So what does the I see? Well, it sees just small RO. The I is here, right? And so what does it see? What does the ohm meter measure? Small RO. What does the test source V test over I test equal? Small RO. So that's our first rule. Let's go back to the rule text. The resistance seen looking into a MOSFET drain with gate and source at DC levels is equal to small RO. Before we apply this, let's try it on a small example. So this is VG and it's pure DC. This is VS and it's pure DC. If I'm looking into the drain, I'm doing signal analysis, small signal analysis, and I want to see the resistance looking into the drain, then I would see a small RO. Why? Because this is VG pure DC. This is VS pure DC. So I can apply the rule. It's a rule now, so I can apply it. If I want to find the resistance seen looking into the drain when the gate and the source are at pure DC levels, then I will see a small RO. Okay, let me consider a simpler circuit. Let me consider a resistor R to ground, and I want to find the resistance seen looking into this terminal of the resistor. Can you type in the chat window, what would I see? I want to find the resistance seen looking into the terminal of the resistor. So the I is here. What would the I see if you're looking into the resistor to ground? Type your answer in the chat window. All right, great. You're all answering capital R, and that's the correct answer. You would see just R, right? Because if you imagine that the I is an ohm meter or the I is a test source and you want to find V test over I test, it will be just R. Great. Let's try another example. And let's take a MOSFET. Like this, with some DC voltage here and a resistor here, which is R. Okay, and my I is here. What would the I see now? So type your answer if you have a guess in the chat window. R in parallel with small RO. That's correct. So if I have such a situation, I would say that this is my first resistor, and it will be in parallel with whatever I see looking into here. So this I would see R in parallel with whatever we have here, whatever the second I would see. So this second eye is looking into the drain of the MOSFET with gate and source at DC levels. So my second eye here at the drain, according to the rule that we just came up with, will definitely see small arrow. This is a rule that we derived. So this second eye, the small eye, would see small arrow. The big eye would see R with whatever the small eye is seeing in parallel with small arrow. So big eye will see R parallel RO. All right. What about if I have two resistors, R1 and R2, parallel with, and they're connected like this. So not just R, but also R1 and R2. And this is really easy. Again, the eye will see R2 in parallel with R1 in parallel with what the small eye is seeing. So it will be R1 parallel R2 parallel small RO. Okay, what about this case? What does the eye see? Again, the eye is an ohmmeter. It will see the series combination of R1 and R2. So R1 plus R2, bravo. What about this? What is the eye seeing? What would the eye see? And again, it will see R1 plus small RO, not parallel with small RO. So the big eye will see R1 in series with what the small eye is seeing. What is the small eye seeing? It's looking into the drain of the MOSFET with DC here and DC here. So this is small RO. And therefore the big eye will see R1 plus small RO. Okay. Notice that we're not doing any small signal analysis. We're just applying a very simple rule. Just applying the rule that we derived. Okay. And of course, some the resistor combinations from circuits parallel series. So there is a question, why is it plus? Well, again, I'll repeat, the big ohmmeter, the big eye is looking into this. So it's measuring R1 with whatever comes after it in series. What comes after it? Well, I have the eye here. So now I have like a smaller ohmmeter looking into the drain of the MOSFET with DC at the gate and DC at the source. So it will see small RO. So the big eye is seeing R1 plus whatever is after it, which is what the small eye is seeing, which is small RO. So R1 plus small RO. Now, here's a tricky one. So let's see if you can answer this one right. What does this eye see when I have the MOSFET and a resistor R between its source and ground? Think about it. Okay, I'm seeing answers like small RO or R plus RO or R parallel RO or infinity. And they're all wrong. Why? Because the big I will see first what the small I is seeing. Small I here at R sees the small I, sees R, right? So that's easy. The small I will see R. But what about the big I? It's looking into the drain of the MOSFET. So that's good. With gate at DC, that's good. However, the source in this case is not at DC. There is some signal at the source because of the resistor between the source and ground. What does this mean? It means that I cannot apply the rule. If the conditions for the rule are not there, I cannot apply it. The conditions for the rule state that the gate should be at signal ground, the source should be at signal ground, and then you can find the resistance seen looking into the drain, and it will be small RO. Here, there is a condition which is not satisfied, and therefore, I cannot apply the rule. The condition that is not satisfied is that the signal at the source is not zero. If I want to use the rule, the signal at the source should be zero. Now it's not zero. So I cannot apply the rule. I cannot say that looking into the drain, I see small RO. No, I will see something else. So what is the answer? Well, the rule doesn't apply, so we'll not use it. If I want to find this, it's like calculating a new quantity. I will do a full small signal analysis, and then I will get the answer. I don't have a rule for that so far. So make sure that if you're applying a certain rule, you're satisfying its conditions. So let's try to apply the rule to find the output resistance of this amplifier we just learned about today. So the output resistance of the amplifier is what? It's the resistance looking into the output, right? If I connect a test source here, so here's my I at the output, and I'm looking back into the amplifier. The small signal resistance seen looking into the MOSFET drain. Now this is the rule. I know about it. How can I use it here to find the output resistance? So the output resistance is what this I is seeing. Now, if you follow, you will find that you reach the drain here, and then you have two branches, one going up and one going down. So the I will see this going down to ground, and this will go up to signal ground. So this I1 will see something looking down, and this I2 will also see something looking up. It's also looking up, but towards ground, because this becomes signal ground. So let's start with Q2. And what does I2 see? I2 is looking into the drain of Q2. This is the drain of Q2. And what's at the gate of Q2? Pure DC. What's at the source of Q2? Pure DC. So this rule, therefore, applies directly to Q2. I2 will see small RO2 because it is looking into the drain of a MOSFET with gate and source at DC. All right. What about I1? What does I1 see? I1 is looking into the drain of Q1. This is the drain of Q1. And with no signal here, so this is 0 DC and 0 signal. But there is the input here. So can I apply the rule? I cannot, in general, I cannot apply it because there's the input voltage. But just because I'm finding the output resistance, and in the condition of calculating the output resistance, there is something very important. We set VI to 0. So this should be 0 if I'm doing only if I'm doing output resistance calculation, which is the case here. So because I set VI to 0, this becomes like as if it's a pure DC. And if there's no signal here, it's as if these are pure DC levels. And I1, because I am finding the output resistance, I1 will see small r01. Because I'm finding RO. And when I want to find RO, the output resistance, I set the input to 0. All right, so I1 is looking down and it sees small r01. So small r01 to ground. I2 is looking up and sees small r02 also to ground. So what does big I see? Big I will see R01 from this to ground and R02 also from this same node to ground. And therefore it will see R01 parallel R02. So R02 looking up, R01 looking down, and R is R01 parallel R02. Again, because I'm doing output resistance calculation. If I'm not doing output resistance calculation, then it will be something else. We cannot use the rule.